Stanford University.
I'm going to do something now I've wanted to do for years. I've really wanted to do this. Okay. Ladies and gentlemen, people out in the audience viewing this from afar, we're now going to stop for a commercial break. I want you all to go out and buy my book, The Black Hole War, My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics. In that book, you will learn about the cruelty of theoretical physicists. You will not only learn about Schrodinger's cat, but you will learn about Suskind's fish and how he flushed them down the toilet. Audience, please. Yeah, come on. All right, now back to our program. You may remember that when we last saw Alice and Bob, Alice was crying bitterly because the cruel Bob was forcing her to learn group theory. Alice, sad to say, is not finished. Bob is not finished with her. Tonight we will see Alice suffer more. Okay, are there any questions about group theory for the moment now that we're back to the story, main storyline? Any questions about group theory? We're not finished with it. We're really not finished with it. Yeah.
There's two parts of your expose on group. It seems to be some kind of abstract mathematical object that has some kind of multiplication table.
Right.
And there's also the part on how those groups act on various objects.
Right.
Can we dissociate the two, or is it?
Well, they're completely related. There's the abstract notion. Let's take the case of the rotation of a spin. All right. There's a perfect case to study. There's the abstract, completely abstract notion of a rotation in space. And I don't tell you what it acts on. I just tell you that is an operation that you can do. Right? Physics has to respect the symmetry under the rotations of space. Right? And so we must then say, how does the rotation of space act on the quantities which are physically relevant? Right? If we were talking about classical physics, we might just say that the rotation of space rotates the coordinates of a particle. It might rotate the direction of a magnet, whatever it does. We know how to describe that. We describe that we know how to describe that. In quantum mechanics, the states of a system are always represented by a linear vector space. There's the abstract notion of a state of a system, and there's the concrete representation of it in terms of column vectors. How big are those column vectors? What's the number of entries into the column vector? Well, that depends on the system, but basically it's the number of mutually orthogonal possibilities for that system. If the system in question only consists of an electron spin, then there's only two states, two mutually orthogonal states, spin up, spin down. If it's two electrons, and again we're only interested in the spin, then there would be four states, two up, two down, one up, one down, one down, one up. If we're talking about a more complex object, for example, the entire motion of an electron, its position as well as its momentum, then there are an infinite number of states. The number of states that it takes to describe the orbital location, the number of mutually orthogonal states of an electron, speaking now about its position, is infinite. It could be anywhere in space, or you could choose to describe it in terms of momentum. So the column vectors describing an electron's position are infinite dimensional. An amplitude for every possible location or for every possible momentum. So there must be representations of the rotation group, of this group of rotations, which are infinite dimensional matrices. And they are. They are. Just what are the matrices which act on the column vectors which describe the system that you're interested in? The size of those matrices will depend on the number of mutually orthogonal states. All right, so let's come back. Spin of the electron. Throw away everything else out of your head. Spin of the electron, 2 by 2 matrices. The group elements are the abstract rotations. They're represented by 2 by 2 matrices. A spin 1 particle. A spin 1 particle has 3 mutually orthogonal states. The rotations are represented by 3 by 3 matrices. In that case, those 3 by 3 matrices are familiar to some of you. They are the 3-dimensional matrices which mix up the components of 3 vectors. What comes after spin, after 3 halves? All right, 1 half. Well, first spin 0. What about spin 0? Spin 0, rotations don't act on at all. They just leave it alone. Okay? So it's completely trivial. You can think of it in some very useless sense that, that rotations act on a spin 0 just to leave it alone. Okay. That corresponds to 1 by 1 matrices. Just the unit matrix, that's all. Just the unit matrix, does nothing. 2 by 2, that's spin a half. 3 by 3, that's spin 1. 4 by 4, that's spin 3 halves, and so forth. So the same abstract group element, the same abstract symmetry operation may have many matrix representations of different dimensionality. That's an important fact. And we're gonna spend a little more time on it. But let's just review for a moment what the symmetries. We talked about the symmetries of rotation of space on a spin a half particle, in particular on a spin a half particle. And we said those rotation operations become represented by matrices which I called U. U because they're unitary. So these are 2 by 2 unitary matrices. I won't bother being more specific than just putting dots there. Those 2 by 2 unitary matrices act on the state vectors of a spin a half. Again, I won't be more specific than writing that. Let's erase it for the moment. And this is called a representation of the group. It's in one-to-one correspondence with the group elements, matrix multiplication, group multiplication. They're in one-to-one correspondence. Let's just flesh it out. What does it mean for a matrix to be unitary? It means that its inverse is its Hermitian conjugate. But we know that the number of degrees of freedom, the number of parameters in a unitary 2 by 2 matrix is how many? How many did we say there were? 8 to begin with. 4 elements, each complex. That's 4 elements. This is 4 equations. That cuts you down to 4. But there are only 3 independent parameters, the 3 Euler angles, if you like. The 3 angles describing the 3 things describing a rotation, namely the rotation angle and the 2 parameters which determine the direction of the rotation. So there are only 3 independent parameters of a rotation. These matrices have 1 too many parameters. And to get rid of that 1 extra parameter, 1 more condition, and that's that the determinant of U, I'll just represent that. We could write it as det, but I'll just write it as absolute value, but it's not really absolute value. It's a symbol for a determinant, that is equal to 1. Now, a unitary, simple fact, incidentally, that when you multiply matrices, the determinants multiply. The determinant of the determinant of the product of A and B is the determinant of A times the determinant of B. All right. It is also true that the determinant of a Hermitian conjugate of an operator is the complex conjugate of the determinant of the original operator. So here's what we can say. Let's take the determinant of both sides of this. The determinant of both sides of this is, first of all, the determinant of u dagger u, but that's also equal to the determinant of u dagger times the determinant of u. And what's the determinant of 1? 1 is equal to 1. 1 here, of course, means the unit matrix, all 1s on the diagonal. All right, now, next thing is the determinant of u dagger is just the determinant of is the determinant of is the complex conjugate of the determinant of u. All right? And if the determinant of u is 1, the determinant of u dagger is 1, and the whole thing is consistent. The only point is that it is consistent. It's a consistent condition on u's. That's, when I say consistent, I mean that it's consistent with the law of matrix multiplication. Right? If you take a bunch of unitary matrices, every one of which has determinant 1, and you multiply them together, you'll again get a thing with determinant 1. All right, so it's a mathematical theorem, which may not be too surprising for many of you, that the special unitary matrices, 2 by 2 matrices, which have 3 parameters in them, special means that u dagger u equals 1, that the group of those matrices is identical to the group of rotations in 3-dimensional space. Now, it's not quite true. Go ahead.
Is there nothing that says that the determinant has to be real?
No, the determinant of a...
It just has to be radius 1.
Yeah,
Complex number radius.
right. The determinant of a unitary matrix must be a pure phase. Okay, that's just from the fact that it's unitary. Okay, from the fact that it's unitary. But you can take any, all right, here's the point. You can take any unitary matrix. Let's suppose its determinant is e to the I theta. You can then multiply that unitary matrix by, well, you'd multiply it by e to the minus I theta over 2, because when you calculate the determinant, you multiply 2 elements together. All right? So if you took u and multiplied it by e to the minus I theta over 2, you would construct a special unitary matrix. All right, so the point is, the extra phase that's in there is almost trivial. You can always get rid of it by a redefinition of u. And in fact, the rotation group doesn't contain this piece here. It's just isomorphic to the matrices with determinant 1. Okay. I told you a little fib when I said that SU2 is exactly the same as the rotation groups. It's not exactly. There's a 2-to-1 correspondence instead of a 1-to-1 correspondence. The unitary operators u and minus u, if u is a unitary operator, u dagger u equals 1, so is minus u, whatever u is. All right? In fact, there's a 2-to-1 correspondence. The matrices u and minus u both correspond to the same rotation in space. But that's a fine point which is not going to play any special role in what we say, at least for the time being. So a simple statement, which is almost true, is that there's a correspondence. Certainly there's a correspondence, but that there's a 1-to-1 correspondence, not quite true. It's 2-to-1 correspondence between the unitary matrices, 2 by 2 matrices, the special unitary matrices, those with determinant 1, and the group of rotations. So for that reason, the electron spin, or the electron wave function, is called a doublet. and it's acted on by 2 by 2 matrices. Now let's talk a little bit about the generators of a group. I think we actually talked about it, but let's be specific about it again. The generators of the group, when you have a symmetry, and the symmetry is represented by a set of matrices like this, then there's a concept of the generators. The generators have to do with infinitesimal elements of the group. An infinitesimal element of the group means, in the case of rotation, a rotation about some axis by a very, very small angle. In other words, it's an element of the group which is very close to unity. Unity means no transformation. Elements which are very close, which are just very small shifts of angles and so forth, are called infinitesimal elements of the group. And the generators of the group are very closely related to these infinitesimally small operations. Now, one of the reasons that the infinitely small elements are important and interesting is because you can build up any element out of a sequence of small ones. In other words, if I want to rotate about some angle by a finite rotation, I just think of it as a multiplication of a bunch of infinitesimal ones. So if you know the properties of the infinitesimal generators, you can put together the entire structure of the group. We're not going to do that. We're not going to study that today, but we are just going to define the generators of the group. And the reason we're going to define the generators of the group is because they really are the conserved quantities. They are the quantities that are conserved and which play the role of conservation laws once you know what the symmetry group is. Okay, so let's define them. Incidentally, for what I've written here, there's nothing specific to SU2. This could be SUn, where n is the number of elements, the special unitary n by n matrices. They're, of course, not all isomorphic to rotations. It's only the SU2 group which is isomorphic to rotations of space. SU3, SU4, SU5, not so easy to visualize. Okay, so here we have the definition. And now let's take an element which is very close to the identity. It doesn't have to be SU2. Let's write it. U is equal to the identity, 1, plus something small, and let's put an I in for simply notational simplicity. It'll simplify notations. A small parameter epsilon, and a quantity which is often, I'm not going to call it G for generator, because we've already used G for group element. And so therefore I will use T. Why T? Beats me, I don't know. So U is 1 plus I T. What is T? Let's find out what we can learn about T. We use the fact, first of all, that U dagger U is 1. All right, so U dagger U, that's 1 plus I epsilon T. Oh, incidentally, it's easy to prove that if U dagger U is 1, then U dagger is 1. I won't prove that for you, that U and U dagger always commute with each other. Not for all operators, but for unitaries. So it doesn't matter which order you multiply. All right, so it's 1 plus I epsilon T times 1 minus I epsilon T dagger. If this is U, then this is U dagger. I gets changed to minus I when you complex conjugate, and this is supposed to be equal to 1. Let's retain things only to the lowest order in epsilon. Epsilon squared is too small for our interest tonight, so let's just keep things to order epsilon. And that says 1 times 1 cancels the 1 there, and it says that I epsilon times T minus T dagger is equal to 0. Or, to simplify, it just says that T is equal to T dagger. What's an operator that's equal to its own conjugate? Hermitian. And Hermitian operators in quantum mechanics represent observables. Right? Hermitian operators represent observable quantities. For the case of rotations, what are these T's? What physical significance do they have? There are three of them. First of all, why are there three of them? There are actually an infinite number of them, but there are three linearly independent ones. So let me explain why that is. The reason is because the rotation group has only three parameters. There's only three independent ways that you can rotate. You can rotate about the x-axis. So I could have made an infinitesimal rotation about the x-axis. I could have made an infinitesimal rotation about the y-axis or the z-axis. And in fact, for an infinitesimal rotation, if I wanted to rotate about some other axis, what I could first do is rotate a little about the x-axis, and then a little about the y-axis, and then a little about the z-axis. Another way to say it is that the generators behave like vectors. If I want a vector in an arbitrary direction, in other words, a vector rotation about some axis, in an arbitrary direction, the way I can think of it is making it up out of the components, the component rotations about the x, y, and z axes. So there are three independent directions that you can rotate in, and three independent, linearly independent t's. Oh, we missed one point. Come back. Back up. There is this condition here, the condition that the determinant is 1. All right, so let me tell you before, we'll get back to it in a moment. The determinant being 1, the determinant of any matrix which is of the form 1 plus, let's call it epsilon times a small matrix, the determinant of M is equal to 1 plus epsilon times the trace of small m. The determinant of a matrix which is close to the identity is 1, that's just the identity, and then the small deviation is epsilon times the trace. That's something to prove. When you go home and prove that. But we can see what that means immediately. It means that the trace of t is 0. The trace of t has to be 0 in order for the determinant of u to be equal to 1. All right, so that's the second condition. The trace of t is 0, and it should be Hermitian. How many independent Hermitian 2x2 matrices are there with trace equal to 0? The answer is 3 of them, and they correspond to the rotations about the 3 axes. But more abstractly and generally, the generators of the group of rotations are the angular momentum operators for a system. So that's what angular momentum means in quantum mechanics. It is the generators of the rotation group, and you act with the angular momentum, or 1 plus I epsilon times the angular momentum, to rotate a system, a small amount, and then if you want to rotate it a large amount, you just do it over and over again. So everything is contained. All the information about the structure of the group is contained in the generators. In fact, it's contained in the commutation relations of the generators. Those are the important things. I won't go into them again. We did commutation relations of angular momentum. I just wanted to connect things up a little bit for you. But the important thing is that the conserved quantities associated with the symmetry are the generators. And
so there are three independent 2x2 matrices.
Say it again.
There are 3 independent 2x2.
Traceless 2x2 Hermitian matrices.
2x2.
Yeah, they have a name.
Pauli matrices.
The Pauli matrices. Yeah, the 3 Pauli matrices.
And then if you went to 3x3 matrices.
3x3 unitary matrices.
Unitary, traceless.
And there are 8.
Like the Gelman.
Yeah, they're the other Gluon matrices, right? We're going to do that in a moment. Right. That 8 is the same 8 as the 8 gluons in the 8-fold way. Actually, that's actually a different 8. Not because it's It's mathematically the same, but it's associated with a different SU3 symmetry than color. But yeah, mathematics is the same. Okay, so that was a little bit about, or a little review, the sorrows of Alice. Let's torture Alice even more. Let's go to SU3. All right. SU3, the pattern is exactly the same, except we're talking about 3x3 matrices. In fact, I'm not even sure that there's very much more to say about it, other than doing some counting and finding out how many independent generators there are. So to do the counting, it's very easy. A 3x3 unitary matrix has how many elements? How many? 18. Starts with 18. 18 independent, 9 independent complex numbers. That's 18. But then we have u dagger u equals 1. Now this really is a equation for each element. This is a product. This is a matrix product. So we can think of it as ij. And this is delta ij over here. How many equations is this? This is 9 equations. So we have 18 minus 9 is 9, but then one additional equation that the determinant is equal to 1. That's 8 equations. And so we can guess that there are 8 different, if we start with the unit matrix, in how many distinct directions in the group space can we deform away from the identity? And the answer is 8, the implication being there are 8 linearly independent 3x3 traceless Hermitian matrices. Traceless Hermitian matrices, the number of parameters is 8. So, and we're going to come back to that. But before we do, let's talk a little bit about how representations combine to form new representations. Now, what we're talking about here is combining systems together to form new systems. In the case of spin, we might be talking about combining more than one particle together to create some sort of composite, for example. And that composite would also have a spin. Let's not worry about the motion of the particles. Let's just think of them as things that we staple on top of each other so they're nailed down to each other. But each one has a spin. So each one has a spin. And let's suppose that we take 2 such particles. We put them on top of each other, 2 half-spin particles. What do we get? Well, we get 4 possible states. But those 4 possible states can be thought of as a basis in that 4 particle states can be thought of as a spin 0 object and the 3 spin 1 objects that the 2 half spins can make. If we take 2 half spins, we can certainly make a spin 1. Why? We can line up the spins in the same direction. So the z component of spin can be 1, it can be minus 1, and it can be 0, but it can be 0 in 2 ways. All right, but still, a spin 1 particle only has 3 states. So one of those 2 ways of making 0 must not be part of the spin 1 multiplet. What can it be? It can only be spin 0. Why spin 0? Because there's nothing for it to transform into. So there are 3 combinations which form the spin 1 multiplet and 1 which forms the spin 0 multiplet. When you combine spins together that way, there are 2 possible total spins you can make. So if you were to take an atom made out of 2 half-spin particles and ignore the orbital motion altogether, one possibility is that the spins are in the same direction. That would give you spin 1. And the other possibility is that they are in the opposite direction, in which case it would be spin 0. It's ortho and para-hydrogen, in particular for the hydrogen atom, where the 2 spins would be the proton and the electron. Right, so you combine, it's important to know how to combine spins and to know what you get, what possibilities you get when you combine them together. What happens in SU3? Now we want to jump to SU3 and discuss some very specific representations of SU3. They're the important ones, which we will discuss. First of all, there is the triplet. The triplet is simply, if U is a 3 by 3 matrix, then it has to act on a thing with 3 components. In the present context, the 3 components represent the 3 colors of a quark. So we're talking now for the moment about one quark, not 3 quarks, one quark, and that quark can be red, yellow, red, blue, or green. It can be red, blue, or green. This is the amplitude that it's red, this is the amplitude that it's blue, this is the amplitude that it's green. And what does the group do to them? It mixes them up. It mixes up red, blue, and green, takes any particular state and sends it to some quantum superposition of states of mixed color, shall we say. So if we took a red quark, that would be like an up spin, 0, 0, 1, and we rotated it by this SU3 operation, we would get something of a mixed character, which would have amplitudes for being red, blue, or green, some quantum superposition. So that's the meaning of these operations. But it's interesting and important to know what happens if you combine representations together. Wait, let me go back a step. Now we want to talk about the various representations of SU3. The representations of SU2 are the spin states. Spin 0, a half, 1, 3 halves, 2, 5 halves, and so forth. Those are the representations of rotations. We want to know something about the representations of SU3, and I'm not going to tell you very much, just a very little bit. There are rather 3 important representations for our purposes. One of them is just a 3-dimensional representation, and it can be thought of as the 3 components, the 3 things that go here, could be thought of as the 3 field operators for, let's call them quark, red, quark, blue, quark, green. We can either think of these matrices as mixing up the states of a single quark, or we can think of it as mixing up the field operators that create single quarks, red, blue, and green. All right. Now, next, this representation by 3 by 3 matrices that acts on the quarks, that representation is called the 3. In the same language, if you use the same language, you would call the half-spin particle of SU2, you would call it the 2. 2 for 2 states. Okay? So the 3 is a representation that's identified with the quark field itself, or with quarks. Now, there are also antiquarks. Antiquarks, their field operators are the complex conjugates of the quark operators. So you can ask yourself, if there is a matrix which acts on Q to give some new thing, we could complex conjugate everything. We could complex conjugate everything, and we could say, let's write it. If, let's call it U is a 3 by 3 matrix, if it acts on the column vector Q, I'm now being schematic, U is a 3 by 3 matrix, Q is a column vector. If it acts to give, let's call it Q prime, the rotated Q, then what is it that acts on the complex conjugate, or the Hermitian conjugate field operator? That's the object which represents antiquarks. Well, it's quite obvious. It's going to be the complex conjugate, not the Hermitian conjugate, the set of elements. If U is a bunch of elements, then U star is nothing but the complex conjugate elements. Let's call it star. Let's call it star to be consistent. So there is a second representation of SU3, which is the set of matrices which are the complex conjugate matrices. For every matrix U, there is a complex conjugate, and that defines a second representation. It's called a complex conjugate representation. It is the transformation property of antiquarks, and that representation is called the 3-bar. This is very abstract, but what is it in the case of electrons? What does this correspond to in case of electrons? It is simply the fact that if the electron wave function gets multiplied by e to the I theta, then the positron wave function gets multiplied by e to the minus I theta. They transform with complex conjugate group elements. Okay? So you would say that the electron and the positron are complex conjugate representations of the U1 group. That's the language. The quark and the antiquark are complex conjugate representations of the group SU3.
It would be the complex conjugates of the Pauli spin matrices,
For the case SU2. Yeah. Now, SU2 is a special degenerate case where the complex conjugate is equivalent to the original matrices by another matrix, and it's a special case. It's called a real group, but this is not important for us now. The 3 and the 3-bar representation are quite different. I mean, they look very similar to each other, but they are distinct. They should not be thought of as the same representation of SU3. They're quite different. And in fact, the generators of the 3-bar representation are the negatives of the generators of the 3 representation. Okay? That's not too hard to prove. That means they carry the opposite color. If a quark carries a red color, then an antiquark carries a minus red color. Okay. Or has the opposite value for the generators. All right, so these are the quark and the antiquark. Now, what happens if you take a quark and a quark, 2 quarks, or a quark and an antiquark? Just like you could take 2 electrons and make a spin 1, which was a triplet, not got to do with this 3, but the triplet of SU2, just like you can make a spin 1 or a spin 0, you can do some similar things with 3 and 3-bar. You take 2 quarks and put them together, you can call that 3 times 3-bar. Sorry, 3 times 3. 2 quarks are 3. This is just a notation. 3 times 3 means 2 quarks. Sometimes this is represented by a circle to indicate that you're not actually multiplying numbers. You're simply building a space which is now a space of 2 quarks. It has 9 independent states. Red, 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 blue, red, green, and so forth. All 9 states. And if you work out what representations of SU3 appear when you multiply 3 by 3, the answer is, first of all, there is an antiquark representation. That's going to prove to be interesting, that if you take 2 quarks, you make something whose color is the same as an antiquark. That's a little bit odd, don't you think? But it's true. It's true anyway. And one more representation called the 6-dimensional representation of SU3. We're never going to need the 6-dimensional representation, but there is a 6-dimensional representation of SU3. I can tell you what these things correspond to. If you think of the quarks as just indices, color indices, then you can combine the 2, well, let's think about you combine the 2 quark states symmetrically or antisymmetrically. You can combine them symmetrically or antisymmetrically. Antisymmetrically gives you the 3-bar, symmetrically gives you the 6. But this is not terribly important. The point is, if you make 2 quarks somehow in the laboratory, the transformation properties of the 2 quark system under this SU3 there will be one term or one way of combining them together, 3 independent states of that system, which will be like an anti-quark, and the other one will be this mysterious 6, which we don't give a damn about. We'll see why as we go along. Now, what happens if we take a quark and an anti-quark? If we take a quark and an anti-quark, what we get is different than what we get when we get a quark and a quark. We get, again, 6 and 3 is 9 states, but it's not the same 9 possibilities. First of all, we make an object which is a 1. What is a 1? That's a thing which is completely invariant under the color operations. Roughly speaking, it's a red plus a red anti-red, quantum superposition of red anti-red, blue anti-blue, and green anti-green. That's one thing, and that's a single representation, and it simply does not transform under the SU3 group. It's called a singlet, an SU3 singlet. And one way of saying it is it's the analog of combining together 2 electrons to make a spin 0 state. It's like a spin 0 state. It does not transform under the rotations. It doesn't transform at all. It's just one state, so how could it transform? There's nothing for it to transform into. So when you take a quark and an anti-quark, there are 9 states, one of which, one linear combination, red anti-red plus blue anti-blue plus green anti-green, that just forms a singlet. And then there are 8 others, and those 8 others are called the 8-dimensional representation of SU3. That 8, incidentally, think about that 8 for a moment. We've seen 8 in another place. It was the number of generators. Right? Just like the number of angular momenta. When you rotate space, the angular momenta rotate into each other. When you rotate in color space, the 8 generators get mixed up with each other. The way the 8 generators transform is called the 8-dimensional representation of SU3. This is sometimes called the adjoint representation. The words don't matter. It's just a representation that transforms the same way as the generators. Okay? And that's what you get when you multiply 3 cross 3 bar. Finally, one other operation. What do you get if you take 3 quarks? 3 cross 3 cross 3. You take 3 quarks, there are 27 states. Well, you can do it in pieces. You can say, if I combine together these 2 quarks, what I will get is either a 3 bar, which is an anti-quark, or a 6. So 2 of these quarks together will necessarily either transform as an anti-quark or as a 6. A 6 is a peculiar representation, which I said we won't care about very much. Now, what happens if you take this product and now cross it again with 3? In other words, we see what we get when we combine 2 quarks. Here's what we get. And then we combine it again with another quark. We will either get what appears if we take a quark and an anti-quark, but we know what that is. That's 1 plus 8. The plus here just means or. You either get a 1, the singlet, or an 8. Just like saying you either get spin 1 or spin 0. That's what this plus means, or. When you multiply 6 times 3, I think you get an 8 plus a 10. But this, again, is not very interesting to us. We don't care very much about that. The interesting thing, and the most interesting thing, is when we multiply 3 quarks together, we get the possibility again of a singlet, of a state which is completely colorless. It has no transformation property under the color. It's neutral. It's just like taking a plus charge and a minus charge, which cancel each other. we get the singlet, which has no SU3 transformation at all, and it can be thought of as a combination which simply is invariant under the SU3 group, under the SU3 of the mixing up the quarks. What is it? Can we guess what it is like? I'll tell you what it is. It's just a red, a green, and a blue quark. But you have to be careful. It's a red, green, and blue quark, anti-symmetrized, not important. It's a red, green, and blue quark. A red, green, and blue quark are the singlet. Then there are other combinations, red, red, green, and so forth. They form the remaining states here. But the most interesting one for our purposes will be this singlet here. So we see that when we take a quark and an anti-quark, just with regard to the colors, you can combine the colors in a particular way to get a singlet, plus other stuff. And when you take three quarks, you can combine them together to get a singlet, plus other junk.
Is it the probability of these other things so low that we don't consider it? Or is there a good reason?
The question is what the energy of them is. Okay? And I will tell you, the energy of them is infinite, but we will come to that. Right. The energy of them is infinite, and so they don't appear in the spectrum. Now, how can the energy of them be infinite? And that was a great puzzle, which we now understand, and I'm going to talk about it a little bit. All right. Right. But now, there is one other kind of particle in nature. There's many other kinds of particles in nature. But there's one other particle in quantum chromodynamics. We're talking about quantum chromodynamics, QCD, the theory of quarks and gluons. What, of course, we've left out is the gluon. The gluon is an object, which I think I've told you before, behaves as if it were a quark and an antiquark. With respect to the symmetry, it doesn't behave like a quark and an anti-quark with respect to what happens if you hit it or anything. Just with respect to the color symmetry, its color properties are the same as a quark and an anti-quark, but only the 8. It transforms as the 8-dimensional representation. It transforms the same way as the generators of the group. All right? So again, it is this octet, which is separate from the singlet here. It's the remaining states here, and that's what a gluon is. A gluon is a thing with two indices, like a quark and an antiquark, except a quark and an antiquark arranged into this octet of SU3. So it's not neutral. It itself is not neutral. So let's quark, the postulates, if you like, of quantum chromo, of QCD. Right. It's got an SU3 symmetry, which I won't write down. The quark transforms as a 3, The antiquark transforms as a 3 bar, and the gluon, or the gluon field, as an 8. Because these equations don't really mean anything. Particles can't equal numbers. Particles are particles, numbers are numbers. This just means the quark field transforms as a triplet, the antiquark as the anti-triplet, complex conjugate, and the gluon as the 8, which is a piece of a quark-antiquark. This remaining possible gluon doesn't exist in nature. Do we know why? Not completely. But the important point about it is it doesn't mix up with the other components. And so throwing it away is a mathematically consistent thing to do because it doesn't get mixed up with the other components when you transform the SU3 group. That's group theory as applied to quantum chromodynamics, as applied to quarks and gluons. Another postulate of quantum chromodynamics, and it's not really a postulate, it's a dynamical output of the theory, but let's take it as a postulate and then explore what it means in a moment. And that postulate is all of the particles of nature, the real particles of nature, not quarks and gluons, which are never seen singly, but are always seen in composites, that the particles which can be separated off and examined individually, particles of finite mass, the real things that occur in the laboratory, are all particles, real particles. I don't know, there's nothing not real about a quark, so I hate to call them the real particles. The unconfined particles, the free particles, the liberated particles, or whatever we wish to call them. Free particles are always transforming under the one. In other words, they are singlets. All the real particles in nature are singlets. There is only two independent ways, well, I'll tell you what the ways of creating singlets are. This is mathematical fact now. There are only two fundamental ways of making singlets out of quarks. One of them is to take a quark and an antiquark. All right? That creates a singlet. The other is to take three quarks. Now, you can do other things. You can take a quark and an antiquark and juxtapose it with three quarks. But the elements, the basic, or you can take three quarks and another three quarks. Three quarks in a singlet and three other quarks in a singlet. That will also be in a singlet. But all of the objects that you can make up have the quantum numbers of combinations of things made out of three quarks or a quark and an antiquark. What about the gluons themselves? Oh, first of all, before we do that, let's give these things names. What is an object made out of three quarks? Or a baryon. A baryon, right. Baryon. They always have half spin, and half spin, when I say half spin, that can be 1 half, 3 halves, 5 halves, 7 halves. Why? Because they're made out of 3 half spin particles. What about the quark antiquarks? These are the ones, of course, in the 3. In 3 cross 3 cross 3, there's the triplet, sorry, the singlet are called baryons. The singlet in 3 cross 3 bar, what are they called? Quark and an antiquark? Mesons. Now we left out one thing. Can we make things out of the gluons? Can we make things out of the gluons? Yeah, there's a thing that you can make just out of gluons. In fact, if you take an 8 cross an 8, I told you roughly what happens if you combine quarks together. You could ask, what happens if you combine gluons together, or gluons with quarks? I'm not going to go through the whole list of multiplication tables that you get when you combine all sorts of things, but there's certainly at least one more interesting thing, and that's an 8 cross an 8. This is simply 2 gluons. 2 gluons. Now, it's not obvious. You get 63 states altogether. 8 cross 8. One of them is a singlet. What did I say, 63? 64 states. Did I say 63? Yeah. There are 64 states in 8 cross 8, and the rest of them form 63 things which are a combination of 8s and other things. 8 appears a number of times. I forget which. I don't remember which representations appear, but there are 63 other states. None of them are singlets. Just one way of combining together gluons to form singlets. So you might ask, is there a particle which is composed of 2 gluons? Just 2 gluons bound together into an SU3 singlet? And the answer is yes. They're called glue balls. They're not made of quarks. They don't have any quark content in them. They're fundamentally just a pair of gluons. You can also make 3 gluons, incidentally. It's possible also it's also possible to get more complicated things. But there are glue balls. So the spectrum of hadrons, the spectrum of strongly interacting particles which come from quarks and gluons, consist of baryons, mesons, and glue balls. All of them are color singlets. Color singlets is the watchword. Now, Another fact, you can check this yourself easily. I think we've actually checked it before. Remember now, all we can make is quark antiquark, quark quark quark, or gluon gluon, and combinations of those. What kind of electric charges do we get if we combine 3 quarks? Well, I think we can get I think we can get charge 2. Let's see, we can get 0, 1, and 2. We can get 2 by taking 3 up quarks. 3 down quarks. Sorry, what would 3 down quarks? 3 down quarks is -1. 3 down quarks is -1, and you have -1, 0, 1, and 2. But the important point is you cannot make a fractional charge with 3 quarks. There's no way to take 3 quarks and make a fractional charge. What about a quark and an antiquark? Well, again, you can take an up and an anti-up, or 2/3 and -1/3. No, 2/3 and 1/3. You know what the story is. And you can again make integer charges.
I don't remember you telling us what the charge of the strange was.
It's the same as the charges down. I did tell you because the way that I grouped them. Yeah, it's the same as a down. All of the quarks are either up-like or down-like. And they come in 3 families: the up to down, the charm, the strange, and the top and the bottom. But they're 3 replicas of the same thing. So all you can make is integer charged particles. And so from the point of view of color, the fact that you only have integer charged particles in nature is the same statement as all the particles combine always into SU3 singlets, into color singlets.
Question about that is, that a singlet is like a pair of entangled electrons. Is that any significance here?
Yeah. Oh.
Other than the way you transform them, or?
Well, that is the way you make such states, is to entangle them, very definitely. They are certainly entangled. Does it have any, I'm not sure.
You can't separate them separately and make correlations on them like you can in Bell's theory.
Well, if you can't separate them because they get stuck together, but you can separate them as far as you like, and it'll just cost you a lot of energy. So in principle, yes, they're entangled objects. Not easy to manipulate. You wouldn't want to try to do an experiment of that type with them.
Question? I'm actually having trouble understanding those equations. Not the details of how you get it, but what the operations are.
All right, good.
The left-hand side has got 3 cross 3.
Yeah.
Which is the group 3
The representation 3. Okay, so let me tell you more mathematically what is going on here.
That's sort of my question.
Yeah. Okay. Let's take SU2 first, all right, and take 2 spin-a-halves. We can think of the 2 spin-a-halves in terms of the field operators which create their particles. That's the easiest way to think about it for the moment. All right, so let's just call the field operator psi, and there are 2 components to it: the psi which creates a up spin and the psi which creates a down spin. Let's call them psi I, where I can take on 2 values, either up or down. Okay. Now, supposing we want to create 2 particles. If psi creates a particle, or psi dagger, doesn't matter. If psi creates a particle, how do we create 2? Psi creates a particle. We can think of the 2 components. We can think of it as psi 1 and psi 2, or psi up and psi down. And the SU2 operations act on this. Now, that's 1 particle. How do we make 2 particles? Well, we act twice with psi. But we can act with psi up twice, that creates 2 up particles. We can act with psi down twice, that creates 2 down particles. Or we can do it 1 of each. So let's write psi I, psi j. In fact, these two operators don't really have to correspond to the same particle. Let's even, we could even think of one of them as being the electron, the other being the proton in a hydrogen atom, for example. Let's even give them different names, psi and phi. They might be the same, they might not be, but let's allow them to be different for the moment. Okay? So this now is an object with two indices. It's an object with two indices. It's kind of like a tensor if we were thinking about vectors in three-dimensional space. Tensors are objects with two vector indices. This object is like a tensor in that it has repeated indices. Now, SU2 can operate on it because SU2 operates on psi and it acts on phi. This is a collection of four objects: up, 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 down, down, up, and down, down. So we could lay out those four: psi up, psi up, sorry, phi up, psi up, phi down, and so forth and so on. We could lay them out in an array and then ask what happens when you act with SU2 on this composite object here. Well, they get mixed up with each other. They get mixed up with each other for the simple reason that the psi's get mixed up with each other and the phi's get mixed up with each other. And so certainly these psi times phi's are going to get mixed up with each other. And there's going to be a 4x4 matrix which represents the same action as just going through psi's and phi's separately and rotating them by the group action. Okay. Now you look at these, at the way these things mix up with each other. You look at the way they mix up with each other and you come to a discovery. You discover that the combination, let's see what it is, psi up, phi down, minus psi down, phi up, doesn't mix with anything else under this operation. It just goes into itself. It just goes into itself. This is an easy thing to check. You just see how SU2 acts on psi up. It mixes it with psi down. You see how it acts on phi down. And you check what happens to this particular combination. And the answer is nothing. So this is a singlet. This is a 1. The other three possibilities, what are they? They are psi up, phi down, plus psi down, phi up. This is I have not put in square roots of 2, but you could put in the square roots of 2 if you wanted. This is orthogonal to this. And then there's psi up, and psi down, phi down. What happens when you do the SU2 rotations on these states? They mix into each other. In particular ways, they will mix into each other. This singlet does not get mixed with these three states at all. And these three states mix up among themselves as if they were a spin 1 object. They get mixed among each other, and this is then called the 3. Spin 1 has 3 states. These 3 mix up among themselves. This doesn't mix up with anything. So when you combine 2 half-spin states, that's, well, when you combine 2 half-spin states, you make a 1 or you make a 3, depending on which combination you take. You make a 1 or you make a 3. You make spin 1, you make spin 0 or spin 1. That's the sense in which these equations are being used here. When you combine together a quark and an antiquark, there are 9 different ways to do it. One of the linear combinations behaves in this way here, and it's a singlet. And the others transform into each other. 8 additional objects which transform into each other. So that's the meaning of these equations here. How many of each kind of combination you get?
Is that a unique thing? I mean, do we
This
know
multiplication
it
table is
couldn't be
unique.
2 plus 7 if
Say it again?
Okay, so
You have to know
3
some
pi
group.
cross 3 couldn't be 2 plus 7? Or,
No, you have to know what the representations of SU3 are. We did a bit of work to find out what the representations of SU2 were, and they were all the spin half and spin and integer spin particles. We could spend 2 more weeks studying SU3 and find out what the representations of SU3 are. What matrix representations are there? There are not matrix representations of every dimensionality. There are matrix representations for SU2. There happen to be, for every dimensionality, a matrix representation of SU2. For SU3, not so. There's the singlet, there's the triplet, there's the anti-triplet, there is the octet, the 8, there's a 10, there's a 15, there's a 20. There's a whole bunch of them, but not every number appears in the possible matrices which have the same multiplication table as SU3. So that's a bit of work to prove. We didn't want to go there. I just went there by saying, all right, here's what you get. And, but the real interesting point is the singlets that appear. The ways that you can combine quarks together to get combinations which don't rotate, or which are the analog of electrically neutral. Why do I say electrically neutral? Because electrically neutral are exactly the objects which don't transform under that U1, the things which the phase cancels out of. Remember, go back again to electrodynamics. The things which are electrically neutral are the combinations where all the phases cancel out. If an electron has an e to the I theta, and a positron an e to the minus I theta, then an electron and a positron, the combination of them are neutral, don't transform at all. 2 electrons, that gets an e to the 2I theta. So it's not called neutral, or it's not called, or it transforms under the group. So singlets are important, but you should just think of them as neutral objects with respect to the transformation properties. And
I mean, is there a possibility that you could just show with that singlet, that transformation? Just one example there, is that
oh, we can go through it, yeah.
maybe it's too much.
It is a little too much, but you know, all right, one simple way to see it, I don't know if this will help you at all. If we write, just write this object here, epsilon, you know what epsilon ij is? It's the 2 by 2 matrix, which is the antisymmetric matrix. Yeah, and contract the indices this way, it's, that's equal to this. That's equal to this. And it's easy to prove that this is a, oh, okay, this, I'll just spend a moment at it. In every dimensionality, for matrix dimensionality, there is always an epsilon symbol which has a certain number of indices. For 2 by 2 matrices, the epsilon symbol, and the epsilon symbol is the antisymmetric, the fully antisymmetric matrix composed out of zeros and ones. Okay? All right. Epsilon ij is the 2 by 2 matrix. What about for 3 by 3 matrices in a 3-dimensional? And it's epsilon ijk, requires 3 indices. All right, so I'll tell you right now, if you take an SU3, epsilon ijk, and let's call it, what did we call the quark fields? Q? Qi, Qj, Qk, then you make the 3-quark singlet, which has no color. I, j, and k have to all be different from each other, otherwise this is 0. So that's why I said a red, a green, and a blue make a singlet. Okay. Well, we don't want to make Alice suffer too much tonight.
For what it's worth, I just happened to bump into this in this other book, that 8 cross 8 equals 27.
Oh, let's write it down. Okay, 8 cross 8. All right, so that means when you take 2 8s and put them together, in other words, 2 gluons, you first of all make a singlet. What else?
Plus 8 plus 8 plus 10.
Well, say it again. 8 plus 8 plus 8. Okay, I'll tell you what this means in a minute.
Plus 10 plus
Plus 10 plus 10? Okay. All right, so let's see, is that right? 10 and 10 is 20, and 8 and 8, this should make, what? 8 times 8 is 64.
Oh, it's
No,
plus,
no.
plus 27. It's not equal to, yeah, it's plus 27 at the end.
You say there's a plus of 27?
Yeah.
Does that make 63? I can't tell. 64? Is that 64?
Yeah.
Okay, good. All right. All right, so for your information, this is a fact I know. I know the representations of SU3 up to 27. After, I think there's a 35, but I don't remember. But another 10? We're not up to 60? No, okay. All right. So what this means is, first of all, there is one and only one combination, quantum superposition of states of two gluons, which makes a singlet. One and only one, and that's the glue ball. Then it turns out there are two orthogonal ways of making octets. That's 16 states altogether, but they form two groups, and the first group mixes into themselves without mixing into the second group mixes into itself without mixing into the first, and both of them form octets. Different combinations, different patterns of symmetry of the wave function of the state of the two gluon system. Then there's something called a 10. And again, there are two distinct ways of combining the gluons together to make 10s, but who cares about 10s because they don't appear in nature anyway. And then there's a 27-dimensional representation. How about in 3 cross 3 cross 3? Okay, so there's a singlet. I don't know. I don't know. We had them written down, but I don't remember.
Can I ask a question? Is it fair to say that what happens if you change the sort of the basis of the thing to the, let's go back to the spin 2 case, to the singlet and the triplet and the 2 up, down, down. Then the matrix,
where are we going? Where are we?
Oh, it may have gotten
Here?
reversed. Okay. Yeah, and
All right.
so you have that, and so use those 4 things as a basis. Then the matrix, which describes the operation, factors into a has 1 0 0 0 0, and then a let's see, yes, and a lower part that moves the 3 among themselves. So you can describe it in terms of how the matrix looks.
If you just work in terms of the basis vectors up, 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 down, up, down, down, up, and down, down, then there's a certain set of 4 by 4 matrices which represent the group. All right? But if you work in terms of these linear combinations, this one, this one, this one, and this one, then the matrices have exactly the property that you say. There's a 1 over here, and then 3 by 3 matrices down here.
Right, and the same thing for this other case here. There's a 1.
Yeah, that's right. That's right. The matrices, the big 64 by 64 dimensional matrices break up into a bunch of blocks. Right. It's block diagonal in a particular basis.
In the basis.
Right. In the basis.
Right.
That's right.
Right.
That's right. That's
In
right.
fact, what you're saying is that there exists a basis
Exactly.
in which this complicated matrix
That's right.
simplifies into block diagonal.
That's right. So there are 64 states. So the SU3 operation has to be represented on the two gluon system as 64 by 64 dimensional matrices. Right? But in some basis, those 64 by 64 dimensional matrices are a 1, an 8 by 8 matrix over here, another 8 by 8 matrix over here, then a 10 by 10, I don't have enough room, another 10 by 10 matrix, and then a 27 matrix down there in a particular basis. That's exactly right.
So each one of those doesn't mix the other ones.
That's right. That's right. In the right basis, they don't get mixed. This one doesn't get mixed with this one, doesn't get mixed with this one. They only get mixed together as an 8-dimensional representation.
Is there a label or a name for that type of subset of the total matrix, the total 64 by 64?
That basis?
You mean for this, for a piece of it like this? Well, when you I'm not sure what the right buzzword. I think you're looking for a particular term which is escaping me right now. In fact, I don't think such a term exists, but I know what you mean.
When you say particles, the 10 particles don't exist in nature, and the other sets that you've declared don't exist in nature, so you don't have to care about them.
Well, maybe you shouldn't say you shouldn't care about them, but they won't appear as real particles in the laboratory. We're going to talk about what creates this peculiar situation that you can't have a free quark by itself, but we'll come to that. So let's talk about it a little bit. Incidentally, the quantum chromodynamics idea goes back a long ways. It goes back sometime. I know who it was. It's due to Nambu, to Yoichiro Nambu, and Nambu had the idea about 1962, quite maybe good 10 years before quantum chromodynamics became the standard theory of quarks and gluons. In fact, the whole idea of color goes back to him. He didn't call it color. I don't know what he called it. And the idea of gluons, also in the same idea. And his idea was fairly simple. He understood that if you made color singlets, then you would not get fractionally charged particles. That was his motivation. What do you have to add into the theory of quarks in order to have some dynamics which will forbid particles of fractional charge? So he realized that if the quarks carried this kind of color quantum number, and if the color always had to be a singlet, then you would never get fractionally charged particles. He had an answer to the question of why particles should only occur in singlets, and it went something like this. He said, all right, now we need another postulate, and the other postulate is the connection or the interaction between quarks and gluons. The postulate is that gluons play the same role in quantum chromodynamics that photons do in electrodynamics, but photons couple to the electric charge. The source of the photon field is electric charge. The gluons, there are 8 of them. What are the sources of the gluons? What is the source of a gluon? There must be 8 quantities, 8 conserved quantities, which you can think of as being similar to charge, and each one of them is a source of that particular gluon, of that particular species of gluon. The eight gluons correspond to fields, which are similar in some sense to photons or to the electromagnetic field. The electromagnetic field is sourced by electric charge. What is the source of the gluon field? Well, what 8 quantities do we have available? The 8 generators of SU3, which are analogous to angular momentum for SU2. Angular momentum is a conserved quantity. It's additive. If you have 2 objects, you add their angular momentum. And color really means, when you speak of the color of an object, you're speaking about how it transforms under the group, but the actual thing which radiates, the gluon field is the color itself, or the generators of the color group, 8 of them, and each one can emit the appropriate kind of gluon. The first meaning of this is that if you take a colored object, such as a quark, it's going to be surrounded by a gluon field. So, much like electrodynamics, the quantum chromodynamics replaces the electromagnetic field with a chromodynamic field. But the only thing new about it is that there are 8 such fields. And the 8 such fields transform the same way under that same 8 that's associated with the 8 gluons. Okay, so that's the first thing. Now, the second thing is to know something about the dynamics of electromagnetism. Let's begin with a charge and an anti-charge. A charge and an anti-charge attract each other. The meaning of that is that if you bring them close together, the energy goes down. Right? So a charge and an anti-charge have less energy if they're close together than if they're far apart. That's why they bind. That's why they bind, because the energy of a neutral system is less than the energy of the two charge. Well, the energy of a neutral system is lower than the energy of a charged system as a rule. For example, the energy of 2 plus charges is much more than the energy of a plus charge and a minus charge. How do I know that? Because the 2 plus charges repel each other. You'd have to do work to push the 2 plus charges together. You get work out of letting a plus charge fall towards a minus charge. So here's an example where a system with a net charge has more energy than a system in which the charges cancel out. Another way to think about it is if you have 2 plus charges, the lines of force have to go somewheres. And so there's net field out beyond the object. That net field has field energy. Field energy is always positive. It's proportional to the square of the electric field. And so there's field energy stored in the fact that there are 2 plus charges here. If there was a plus charge and a minus charge, there might be field in between them. And let's suppose you brought them very close together. There might be a little dipole field in there, but there would be no field on the outside. There would be no large field energy on the outside. And so the field energy, or the field energy stored in a neutral system, is less than the field energy stored in a charged system. The larger the charge of the electron, the more profitable it is, let's say, to have a neutral system energetically, or the less profitable or the more expensive it is in energy to have a net charge system. Just the bigger the electric charge, if the electric charge of the electron was 1,000 times bigger than it is, the self-energy of the electron due to the electromagnetic field would be much bigger than it is. In fact, the repulsive force between 2 plus charges would be much, much stronger than it is, and the amount of energy it would take to assemble 2 plus charges would be very much bigger than the energy needed for a plus charge and a minus charge. The huge charge of the electron would then make it very, very prohibitive to have net charge, and very, very efficient, low energy, to have all charges cancel out. So if the coupling constant of electrodynamics were large, very large, we would be very used to the idea that the low energy particles, the low mass is energy of course, the low mass particles in nature, the low mass objects in nature would be electrically neutral. If the charge was big enough, we might never have discovered individual electrically charged particles. They would be confined. It would just be too prohibitive in energy to pull them out of an atom, for example. So what Nambu said is, look, if I have this quantum chromodynamics, and if color, the color generator, or the color degree of freedom, is the source of the gluon field, then if we make the charge, the numerical coupling constant, the analog of electric charge, if we make it large enough, then it will be simply impossible to pull apart these quarks into non-singlet states. A singlet state is the analog of neutral. Pulling them apart, you would be left over with net amounts of color, which would cost you lots of energy. So he understood that when systems were in the color singlet state, they were fully attractive and pulled themselves together. When they weren't, there was always an element of repulsion that meant it cost an enormous amount of energy to pull them together. So that was Nambu's explanation. He said, quantum chromodynamics has a natural way of making sure that the real particles in nature are integer charged and that quarks always come in either the quark-antiquark combination or the three-quark combination. And this was essentially correct. It turned out to be correct, but the dynamics is a little more interesting than that. So let's talk about the dynamics and why the dynamics is more interesting. Any questions up till now? Okay, why is the dynamics more interesting than that? And the reason the dynamics is more interesting than that is because the analog of the photon, the gluon, is charged, carries color. The gluon itself is not neutral with respect to the, remember the neutral piece was this ninth member that we threw away. The 8 gluons themselves are not neutral. They transform under the 8. It's as if they had a color charge. That is why gluons don't appear in nature as objects. The color, they themselves are colored, and because they're colored, they have a big color field around them, and they are prohibitive in energy. But this is interesting. What it says is that the gluon itself is charged in a way that the photon is not. The fact that photons are not charged means they don't interact with each other. They're not sources. A photon is not a source of another photon. Electrodynamics, or at least classical electrodynamics, is a completely linear theory, meaning to say that, that electromagnetic waves just pass right through each other. That's because the electromagnetic wave itself is not charged and doesn't influence other electromagnetic waves. So in electrodynamics, the photon and the electromagnetic wave are very simple and linear. But in quantum chromodynamics, it's much more complicated. The analog of the photon itself is charged. That means that the analog of an electromagnetic wave intersecting another electromagnetic wave will be a serious interacting phenomenon. In fact, even just a single wave of the gluon, one part of it will interact with the other. One part of it may have some color, the other part of it may have some color. Those colors will interact with each other, and the dynamics of gluons is far, and the not just gluons, but the field analogous to the electromagnetic, of the Maxwell field, is far, far more complicated and dynamically interesting, but also much more difficult to understand. It turned out that pretty much the important thing that happens, which is new, can be summarized fairly easily. And I'll summarize it for you on the blackboard in terms of pictures. The equations that go with this, there are equations, but the pictures, I think, are better than the equations. There's a quark, and there is its quantum chromodynamical gluon field around it. Now, in electrodynamics, the different pieces of the photon field or the electromagnetic field do not interact with each other, and so there's no sense in which one field line repels or attracts other field lines. They're just completely independent. They don't interact with each other. In quantum chromodynamics, the gluon field itself is not neutral, and therefore the gluon field interacts with other pieces of gluon field, and the result is very simple. It turns out to be fairly simple. The lines of flux basically attract each other. They attract each other, and they attract each other in a way which makes... Now, the rule about lines of flux is they don't end except on another charge. The lines of flux coming out of a quark or coming out of a color charge attract each other, and in the process of attracting each other, energetically, they want to form tubes. They want to form tubes of flux with the flux running right down the tube. It is more or less, you can either imagine that the lines of flux are attracting each other, or that empty space is repelling the lines of flux and pushing them and squeezing them into a tube. That's what happens. That's pretty much the main effect of the nonlinear interactions between the gluon field, that it makes it energetically favorable to take those lines of flux and bundle them into tubes. Let's suppose that's true now. Now supposing we have a quark and an antiquark. We have a quark and an antiquark. Lines of flux come out of the quark and go into the antiquark. If this were electrodynamics, those lines of flux would separate and form the nice dipole pattern that we're all familiar with, anybody who's ever looked at a magnet and, right. All right. The field energy associated with this big dipole configuration is relatively small because the field gets weak far away. Right? In this configuration, there's a uniform field no matter how far you take these particles from each other. There is a uniform field in between, just exactly as if you took an electric or magnetic field and pushed it through a tube. There would be a uniform field, the lines of flux don't end, and because there's a uniform field, there's a uniform energy per unit length. What's the result of that? The result of that is if you try to separate a quark from an antiquark, the energy just grows linearly with the distance between them. As you pull this out, it's like the gluon field was really sticky, really Turkish taffy. Except Turkish taffy would get thinner and thinner as you stretched it out, huh? So it's not quite like chewing gum with Turkish taffy. It's like a kind of chewing gum that as you separated it, always created more chewing gum in between so that it never got thinner and thinner. There's always a fixed number of lines of flux coming out of every charged object, and they don't disappear. So this tube, it's called a flux tube, or a fluxoid, and the fluxoid has a uniform charge per unit distance. Any charged object, which means any object with non-zero color, any non-singlet, any object which is not a singlet, here it is, it puts out lines of flux. Those lines of flux bundle themselves, and unless they end on an object of opposite color, that object is just going to have an infinite charge because those lines of flux have to go someplace. They'll end at infinity. The cost in energy will be infinite. That's the basic dynamics of quantum chromodynamics. Linear flux tubes like this, which are the ingredients which keep quarks from flying around freely. If you hit a quark real hard inside a meson, this is a picture of a sort of extreme picture of a meson, a quark and an antiquark. You hit that quark hard, it goes flying out, but it simply can't get away. The field energy just increases and increases and increases linearly with distance until you've run out of kinetic energy, and then it gets pulled back. Or something else happens. What's the other thing that can happen? Right. Yeah, right. The other thing that can happen is that the string can break. If this is a quark, and this is an antiquark, then spontaneously out of the vacuum, particle pair production can create an antiquark over here and a quark over here. But you still haven't created a quark. You've created two mesons. So you give one quark in a meson a good shot, you hit it really hard, it tries to escape, and either it can't escape because it runs out of energy and gets pulled back, but actually more likely what will happen is a quark and an antiquark will be created in between, and you'll just create two mesons. If this quark over here is still going too fast, it may still try to escape. It may try to escape this one over here. What will happen? And so what happens when you hit a quark really hard is that inside a meson is that a whole bunch of mesons go flying off, forming what is called a jet.
Do you ever get any other hadrons?
Oh yeah, oh yes, absolutely. You can get anything as long as it's neutral. Right. This is the picture of a meson. The other ingredient that is in quantum chromodynamics is that 3 quarks can exist. This doesn't explain 3 quarks. The 3 quarks are explained by a mathematical fact that the flux lines can come together in 3s. Quark, quark, quark. And, but that's not too surprising because 3 quarks again make a neutral object. 3 quarks again make a neutral object, and that means that if you have 3 quarks, there'll be no net lines coming out of it. So somehow the lines of force that come out of each one of them have to be able to cancel each other. That's quantum chromodynamics. It's based on the SU3 group, and it's called a gauge theory. A gauge theory is simply any theory where the conserved quantities are coupled to a Maxwell-like field, are coupled to a field similar to photons. It has a deeper meaning than that, but for our purposes, anytime there is a conserved quantity analogous to electric charge which functions as the source of a photon-like field, a gluon-like field, that's called a gauge theory. The gauge theories are always based on symmetries. Why are they based on symmetries? Because they're based on the idea of conserved charge, and conserved charge means a symmetry of some kind. Incidentally, what's the connection between conservation and lines of flux? Conservation and lines of flux are intimately connected. If you have a rule, for example in electrodynamics, that every charged particle has to be the source of lines of flux, and that lines of flux can only end on charged particles, then charge has to be conserved. There's no way, remember these lines of force go off to infinity. Well, you could say, I could make this charge suddenly disappear if I allow the lines of flux to simultaneously all disappear. But that would violate the speed of light constraint. You would be able to send a message arbitrarily far distance if by simply removing that charge, you suddenly changed the field at infinity. The fact that you cannot send a signal faster than the speed of light tells you that you can't remove this charge. Why? Because it's sort of anchored by the flux lines at infinity, and if you could remove it, either one of two things. Either you would send a sudden signal far away that the charge wasn't there by removing the field, or you would be left over with these lines of flux that don't end on charges. So if lines of flux have to end on charges, then that's tantamount to saying that the sources of the field are conserved, which in another language says there must be a symmetry. So some symmetries are connected with photon-like fields which give rise to lines of flux. Those theories are called gauge theories. Okay? And you can't even imagine, without breaking the rules of the theory, what it would mean for the charge not to be conserved, because the rules of the theory attach the charged particles to the lines of force. Okay, that's quantum chromodynamics. Now we've actually gone either, depending on how you count, either 2/3 or 3/4 of the way through the standard model. We've gone through 9 generators, if you like. The 8 generators of SU3, and what's the other one? The electric charge, which is not the 9th generator of U3. The electric charge, those are 9 conserved quantities. They couple to the 9 gauge fields, the 8 gluons, and the photon. The Standard Model has 3 more generators, which we will talk about. So we've got 9 out of 12. That's 3/4. The other way of counting is to say we studied SU3. That's quantum chromodynamics. We've studied U1. That's electrodynamics. The Standard Model is SU3 cross SU2 cross U1. We're missing the SU2. The SU2, it's not angular momentum. There's another ingredient in the Standard Model called SU2. We'll start to take up SU2 next time. We've covered a lot of ground, and I think in about 2 more lectures we can probably finish off the basic structure of the Standard Model, SU3 cross SU2 cross U1, put it together into a package, and I think the other element that we need, of course, is the Higgs field. The Higgs field plays an important role there. But I would say within about 3 lectures, we will have the working parts of the Standard Model. And then we can start to explore what the puzzles of it are, why people think we have to go beyond the Standard Model, and why people think there are going to be interesting new things discovered at CERN. I think that's where we want to get. And okay, good.
For more, please visit us at stanford.edu.